Hello students and welcome back. Chapter 14 begins our discussion of solutions, and for most of the rest of this course we'll be discussing aqueous solutions. Here are some equations and relationships. We'll be discussing Henry's law, molarity, molality, concentration in parts by mass and parts by volume, concentration in mole fraction and mole percent, and Raoult's law, and vapor pressure of a solution with two volatile components, freezing point depression and boiling point elevation, and osmotic pressure. Here are some solution concentration terms. We learned about molarity last semester, which is moles per liter of solution. In this chapter, we'll talk about molality, which is moles of solute per kilogram solvent, mole fraction, which is moles of solute per total moles of solute and solvent, and that's going to be in a decimal form. If we multiply that times 100, we get mole percent. Next, we have parts by mass, which is going to be mass of solute over solution times a multiplication factor. We have percent, parts per million, and parts per billion. Next, we'll see some different constants for different substances, which are solvents. We have the freezing point depression and boiling point elevation constants for some different substances, which we'll use at the end of the chapter. The first solution we'll discuss is seawater. As you probably know, drinking seawater can cause dehydration and diarrhea. This is because seawater is a solution, primarily a solution of sodium chloride in water. Seawater is a homogeneous mixture of salts with water, and it contains higher concentration of salts than the salt in your cells. So as seawater passes through your body, it pulls water out of your cells, due mainly to nature's tendency toward spontaneous mixing. This results in your cells' water level being reduced and the water level in your intestines being increased from the liquid flowing out of your cells and into the intestines. Here's an image of what seawater might look like on a molecular level. We have the water in red and white. The red represents oxygen and the white represents hydrogen. We have the sodium represented with purple balls and the chlorine represented with green. The majority component of a solution is called the solvent, and the minority component is called the solute. Homogeneous mixtures are mixtures of two or more substances, where the composition can vary from one sample to another. They appear to be one substance, though really they contain multiple materials. Most homogeneous materials we encounter are actually solutions, for example, air and seawater, like we talked about earlier. Nature has a tendency toward spontaneous mixing, and generally uniform mixing is more energetically favorable. Here's an example of spontaneous mixing. We can have a tank that has pure water on one side and a sodium chloride solution on the other, for example, something like seawater, and these two solutions are separated by a barrier. If the barrier is removed, the solutions will mix because nature tends toward spontaneous mixing. So this is why seawater causes diarrhea, because the water that is in the inside of the cell is more dilute than the water in the seawater. And as the seawater moves through the intestines, water is forced across the cell membrane due to this difference in concentration in order to in an attempt to dilute the solution on the other side. This results in more water in the intestines, and this results in dehydration and diarrhea. Here are some common types of solutions. A solution can be composed of a solid or a liquid or different combinations of those. For example, we have a gaseous solution, which can be a gas in the solute phase and a gas in the solvent phase, and an example would be air. We can have different liquid solutions, for example, a gaseous solute in a liquid like club soda, a liquid solute in a liquid like vodka, and a solid solute in a liquid like salt and water that exists in seawater. A solution can also be a solid like a ring. It can be a solid solute in a solid solvent, for example, brass, which is copper and zinc, or some other alloy. In aqueous solutions, which are most of the solutions we'll be discussing, water is the solvent. So that means water is the majority component. When one substance dissolves in another, it's said to be soluble. Salt is soluble in water. Bromine is soluble in methylene chloride. In other words, there's an old adage, like dissolves like. When one substance does not dissolve in another, it's said to be insoluble. For example, oil is insoluble in water. The solubility of one substance in another depends on nature's tendency toward mixing and the types of intermolecular attractive forces. Nature's tendency toward mixing is also known as entropy. For example, if you had two gases separated by a barrier, and you had a pure gas on each side, when you remove the barrier, the gases will mix. And this is due to the increase in entropy or disorder in the system. This is naturally favorable. Entropy is the measure of energy dispersal in the system, and energy has a spontaneous drive to spread out over a large volume, or in other words, to increase the disorder. By each gas expanding to fill the container, the gas's energy is dispersed over a larger volume. Which statement is true? Ideal gases mix because mixing decreases their potential energy, increases their potential energy, decreases their entropy, or increases their entropy. D. Ideal gases mix because mixing increases their entropy. Here are some types of intermolecular forces. On the left, we have dispersion forces, which exist in all substances, but those are the primary forces in nonpolar substances. Next, we have dipole-dipole interactions which have partial positive and partial negative charges. Then we have hydrogen bonding, which exists between substances that have a hydrogen on an oxygen or a nitrogen generally, and ion dipole interactions, where we have a positively charged substance surrounded by another substance that has partial negative, for example. Let's look at these intermolecular interactions in a little more detail. First, we have van der Waals interactions, or London dispersion forces, and this interaction exists in molecules containing mainly carbon-hydrogen bonds. If you consider the electronegativity difference between carbon and hydrogen, we see here that hydrogen is 2.1 and carbon is 2.5. Anything less than around 0.4 to 0.5 is considered nonpolar, so carbon-hydrogen bonds are nonpolar bonds, and the only type of interaction that can exist there are these van der Waals interactions, or London dispersion forces as they're also known, which exists from or results from the normal movement of electrons in molecules. The next type is dipole-dipole interactions, and these can exist between molecules that have a larger electronegativity difference in their bonds. So let's consider acetone, like is shown here on the left. We have a carbon-oxygen double bond in acetone. So let's draw that molecule. This carbon-oxygen double bond results in a large electronegativity difference around the center of the molecule. You can see here that carbon is 2.5 and oxygen is 3.5, giving this bond an electronegativity difference of 1, which is large enough to be polar. The oxygen is withdrawing electron density toward itself because oxygen is the second most electronegative element on the periodic table next to fluorine, and that results in acetone having a partial positive end and a partial negative end. So if you line acetone molecules up with each other, we have a partial positive end and a partial negative end. The partial negative end can interact with the partial positive end of the next molecule, and so forth. Okay, and that's known as a dipole-dipole interaction. So those can exist between the same type of molecule or different types of molecules, like what is shown here with chloroform. The next type of intermolecular interaction that we'll look at is hydrogen bonding, and this is one of the most important ones, one of the ones that we'll see over and over again. Hydrogen bonding exists generally when you have a hydrogen on an atom like oxygen or nitrogen. So you see here that the electronegativity of oxygen is 3.5 and nitrogen is 3. Okay, now fluorine has electronegativity of 4, and it is known to have hydrogen bonding, but HF is a molecule in and of itself, and fluorine only forms one bond, so we can't have hydrogen bonding if fluorine exists in a molecule because it's not going to have a hydrogen on it when it's in a molecule. So generally hydrogen bonds exist on OH and NH molecules containing an OH bond or an NH bond, so alcohols and amines. So this is because the electronegative oxygen or nitrogen is pulling electron density toward itself, okay, and this results in, again, just like we saw with the dipole-dipole interactions, a partial positive end and a partial negative end. The only difference here is that this bond is specifically called a hydrogen bond because of the large electronegativity difference between oxygen and nitrogen and hydrogen. It's large enough to create a special type of bond, and it's very important for holding these molecules together with these intermolecular interactions and leading to a higher boiling point. Alright, the next is an ion-dipole type of interaction, and you see here that we have a sodium, for example, a sodium ion, which is interacting with, so the sodium ion is positively charged, interacting with the partial negative end of the waters, like we just talked about. So we have this partial negative solvent shell around the sodium. And if we had its neighbor, the chloride could interact with the positive end of the water molecules, forming a network of solvent and solute ions.